Welcome to Lesson 6 of the Teacher and Student Training Series for Biochemistry Literacy for Kids. In this lesson, we're going to be talking about acids and bases, finding out what those things actually mean. So up until this point, we've looked at the atomic structures of some of the first elements in the periodic table. And we've come up with this rule, this 4-3-2-1-0 rule. We also saw that boron is kind of connected to this. We have 3-4-3-2-1-0. So there's definitely a connection between the number of bonds that an element has and its position on the periodic table. What we learn in this unit is that almost all the time when we learn something in chemistry, we always learn something later that changes our ideas of what we learned before. So we're going to learn that these rules, these 4-3-2-1-0 rules, they're not always the case. So we're going to start to see how that works out. Let's first just review our hydrogen bonding model. We have two hydrogen atoms, each has a lone electron. They come together to form a hydrogen molecule because the electrons want to achieve a helium configuration, right? We remember what a bond is. A bond is a shared pair of electrons. And when you're using your model kits to build your atoms, always remember that those gray pieces are representative of a shared pair of electrons. That's our hydrogen gas molecule. There's some issues with nomenclature in chemistry and naming. This can be a little bit confusing for students, so I'm going over it right here. Because today is a lot about hydrogens, because acids and bases, it's actually about hydrogens. Hydrogen atoms are atoms that have one proton and one electron. So two hydrogen atoms comes together to form a hydrogen molecule. Hydrogen molecules, unfortunately, we call it the same thing. We call it hydrogen, whether it's a molecule or the gas. So to be a little bit clearer, I sometimes like to say hydrogen atom versus hydrogen molecule, which is actually two hydrogen atoms connected together. Today we're going to be learning about another subtlety to this idea of what hydrogen is. There's two more forms of hydrogen. Some people may say that protons are a form of hydrogen. We're going to see why that is today. A proton is basically a hydrogen atom that is missing its electron. So we can kind of represent a proton this way. Another form of hydrogen atoms are hydrides. Hydrides are hydrogen atoms that have had, what can you tell added? An extra electron added to that first orbital. You may recognize this configuration as the helium configuration. We have that black square around the helium. All right, so let's review these three different things. All these things are called hydrogens, but they differ in the number of electrons, right? They all have the same number of protons, one proton, so they can all be thought of as hydrogen, but the proton doesn't have any electrons. The hydrogen has one electron, one proton. And the hydride has an imbalance. It has one more electron than protons, right? So if you add up these charges, we're going to see we start to understand the charges of ions. So the first ion we're learning about is the proton. The proton is an ion, which means that it's a charged atom. So protons have a positive charge. Hydrogens actually have no charge. The charge is balanced, right? One proton balances with an electron, and then the hydrides have an imbalance as well. There's only one proton. We can't change the element. We can't add more protons, so the number of protons is fixed. But the number of electrons, because they're on the outside, you can think of them as being able to be changed. So the number of electrons, two electrons, one more electron, one more negative charge. So if you add these two numbers up, you end up with a -1 charge. In chemistry, we tend to not write the 1, although that can be a little bit confusing, so you can write it if you like. We tend to just write plus and minus if we mean +1 and -1. Some more nomenclature. So these are all thought of as hydrogens in chemistry. To differentiate them, we have to write some charges. So the proton, we call it H+. The hydrogen is just H, as we know from before. And hydride, we can actually write H-, or if you want to be more precise, you can write H -, to represent what? To represent those two paired electrons there. That's just another way of emphasizing the fact that we have a hydride. So we're not going to talk really too much about hydrides today. Really, it's just going to be about protons. So later in the lesson, when you see me writing H+, when we talk about protons, always remember that the proton is not really a normal hydrogen. It's a hydrogen that's missing its electron. All right, so let's try to start to talk about the idea of acids and bases. We saw from previous lessons that nitrogen tends to make 3 bonds because it's trying to achieve the neon configuration. We end up with ammonia. Ammonia has this 1 extra electron pair at the top, which is actually going to become really important today. We're going to see why have I spent so much time talking about lone pair electrons. They don't seem to do anything, right? But today we learn what they are going to be doing. So that's our ammonia, and we're going to start writing out those lone electrons because they're very important. Let's look at something else that can happen to ammonia. So that's the 4-3-2-1-0 rule, right? That's the 3. Nitrogen makes 3 bonds. What can happen else with the nitrogen, right? So this is another way of drawing the nitrogen. If you have the 4-hold nitrogen, you can put an extra bond, or if you have the 3D lone pair pieces that some of the kits have, you can put that piece in the 4th hole there and kind of imagine where that lone pair of electrons would be. And it's making this special geometry again. Actually, it looks a little bit like the methane, doesn't it? It's just missing a hydrogen. What can we use that lone pair electron for? We can use that lone pair electron, that lone pair of electrons for attracting what? What are we seeing that's happening here? We're attracting a proton. Doesn't it kind of make sense that lone pairs of electrons could attract protons? Electrons have a negative charge. Even though that ammonia doesn't have an overall negative charge, electrons are negatively charged. And protons, we know, are positively charged because we can see there's only 1 proton, no electrons. So we can actually get this kind of thing to form. This is also favored because why? Before, the proton didn't have any electrons. Now, which electron configuration does it have? It has the noble gas configuration of the helium. So that's probably part of why protons can be attracted to lone pair electrons. So before we only knew about ammonia as that structure, but now we know that ammonia can actually change. It can attract protons because of that lone pair of electrons to form something new. That something new also has a neon configuration. All the hydrogens now have a helium configuration. What is this new thing? This new thing looks a lot like methane, right? But it's not methane. It's a different element in the center. This is called ammonium. So you may have heard of ammonium. Ammonium is actually the acid form of ammonia. We're going to get really comfortable with acid form and base forms today. You should start practice drawing these. This is the structure of ammonium, NH4, right? We're going to contrast the 2 structures. We have the ammonia and the ammonium. Let's kind of figure out what the charges are on these guys, okay? So if you were to count up all the protons in an ammonia, you'd see that it has 10 protons. Why? Because it has 7 protons that are part of the nitrogen, and then 8, 9, 10, 3 more that are part of the hydrogens, right? So we have 10 protons. We also have 10 electrons if you were to count them all up. We have 10 electrons just like the neon, right? Because we have neon configuration. So we have a balance of charge. So we never really wrote charges before because all the molecules that we have been learning about have all been neutral. All the protons and electrons have been balancing. Now it's different. Now we have to think about something else. Let's look at the ammonia. Because an extra proton has been added into our molecule, that means we actually have a surplus or 1 extra proton than we had before. So if your students are okay with negative numbers, this could help. For some very young students, I've found that they're not really comfortable with negatives, so this may not work on very young students, but this might be an opportunity to teach them about negative numbers. If we add up positive 11 with negative 10, we end up with positive 1. There's 1 positive left over. You can just see that there's 1 extra proton. So it makes sense that ammonium has a positive charge. Now we're going to look at these molecules in 3 dimensions so that you can start building them. And we've had a lot of experience with ammonia, but ammonium is a new one for us. Ammonium is reminiscent, or it reminds us of methane, right? It's a molecule that has 1 central atom, 4 hydrogens all equally spaced around. It looks a lot like methane. It has that tetrahedral geometry. Although this is definitely not methane. It's a different central atom, so it's a different molecule. And it also has a charge, so it has different properties as well. Now, what we're going to begin to learn about are the concepts of acid and base. The base form of this molecule is ammonia, and the acid form is ammonium. So what am I talking about the base form, the acid form? These 2 molecules can convert from one to another. So if you build an ammonia, it's actually pretty easy for that molecule to become an ammonium, and I'm going to show you how that works. And if you have the 4-hold nitrogens and either a regular bond or a lone pair molecular modeling piece, you can build this and follow along with what I'm doing here. So what are we looking at here? We're looking at really an ammonia molecule with a proton nearby. Remember, the protons are positively charged. The protons are simply represented by the hydrogen spheres, the little spheres that you have in your kit. Whereas the lone pair electrons can be represented by this bond or by the lone pair model piece if you have those as well. So we have here ammonia, right? Ammonia. This is the one that we've built since the beginning of the course. Let's see what happens if we add a proton on. Now the ammonia molecule has become ammonium. We have the acid form of the molecule. This is a form of the molecule that has an extra proton that's been added to it. The molecule that we started with does not have that extra proton. That proton hasn't been added yet, and that's the base. So a molecule that doesn't have a proton yet, that can have a proton, is a base. And the molecule that has the proton added on, that version of the molecule, is an acid. So acids and bases are actually different versions of the same molecule. So it's a great idea to practice assembling the ammonium from the ammonia. So build your ammonia that includes this extra bond or lone pair piece to it, and practice popping on and off that proton. When you pop it on, you've made the acid, and then when you pop it off, it's the base. It's as simple as that. That's really all it means to be an acid or a base. So this is a really cool activity to help you understand acid and base, and also the connection to charge, right? Protons don't have any electrons. They're only a positive charge. When they connect to another molecule, they bring that extra positive charge with them, so the molecule that they land on ends up with a positive charge as well. That's the connection between base and acid, not charged ammonia, and charged ammonium. If this is a little bit confusing, you're not alone. Almost all the students are confused with the first example, but just like things you've seen in this course before, we're going to do some more examples, and it's going to become clearer and clearer. By the end of the lesson, you're going to be just fine with acid and base. Let's compare these two molecules, right? Ammonia is the base because it doesn't have the proton yet, and ammonium is the acid because it has the proton. And theoretically, that proton could be lost. So here are some definitions of acid and base. Acids are molecules that could easily lose a proton. So that means they have an extra proton that they could lose. Bases, it's the opposite. Bases are the molecules that already lost the proton. Therefore, it could gain it back. So let's now look at carbon. Carbon, as we know from the very beginning of the course, can combine with 4 other atoms, 4 hydrogens in this case, to form a methane molecule because of the tendency to form the noble gas configurations. Here's our very familiar methane molecule, CH4. Looks a lot like ammonia, right? But very differently than the ammonia-ammonium pair, methane does not participate in acid-base chemistry. We don't see protons coming on and off carbons very easily. This is really, really different from nitrogens. If you see a nitrogen, you should always suspect that it may be involved in this acid-base chemistry, that it can become charged or uncharged. Molecules that are solely made of carbon, this does not happen. Carbon molecules do not lose protons, and they also don't gain protons easily because they tend to hold on to their protons. The reason for this is that the bonds between carbons and hydrogens are very strong, and they're very equal. And we're going to talk more about what that means in a later lesson. But for the time being, please just remember that carbons do not lose protons. Therefore, they do not become, they're not acids, and they don't become bases. We're going to come back to this topic later on. If you see a carbon, leave it alone. That's what my point here I'm trying to make. That is very different, though, than oxygens. Oxygens are very famous for participating in acid-base chemistry. We're going to learn a lot about how oxygens are involved in acid-base right now. So let's just review how to create these dot structure versions of oxygen-containing molecules. We also know what this molecule is by now. That's our water molecule. We know that oxygens have 2 lone electrons, single lone electrons that need to bond with something. This gives us our very familiar H2O water molecule that has 2 lone pairs of electrons left over. And you can start drawing the water molecule with those 2 lone pair electrons, because those 2 lone pair electrons are very, very important for many different reasons, but one in particular in terms of acid-base theory. So let's start to look at how can water be an acid or a base. And this is actually a model for how many other molecules that contain oxygen can act as acids and bases. When you see an oxygen, you can suspect that it may participate in acid-base chemistry. It's not always true, but very, very often, oxygens can be a sign that you have either an acid or a base. Do you remember how we made ammonia into an acid previously? What did we do? We had to acknowledge the fact that those two lone pairs of electrons can attract protons that may be nearby, right? Those electron pairs are negatively charged, so we might be able to use them to attract a proton and to form an acid. So let's kind of imagine what that could be. So here's our lone pair of electrons, and maybe a proton approaches those lone pair of electrons. It's not so hard to imagine that they would be attracted, right? And one thing that I haven't actually talked too much about on the bottom here, do you see how the periodic table is changing when I add this in? I'm just trying to show you that the number of electrons that are belonging to the oxygen is changing, right? So right now there's 8 electrons belonging to the oxygen, and when the proton gets added, it's only 7, right? So this is going to give us some hints about charge, as we're going to see in a minute. This is a new molecule, right? This molecule has 3 bonds. It looks really different than water, and it also violates the rule that I told you earlier about how oxygens make 2 bonds, right? So now we're seeing that there's some more subtleties to this. There's some more details that I left out in the simplistic introduction, right? So this molecule, this should look really weird to you, right? Because you're used to oxygens having 2 bonds. This is a special molecule called hydronium, H3O. H3O, right? It's not H2O, it's H3O. Very interesting, right? Let's compare water and hydronium. And I'm very interested in us figuring out the charge on what this hydronium could possibly be. Let's first look at the protons. We know that we have 10 protons because there's 8 protons from the oxygen, 2 protons from the hydrogens. Let's figure out how many electrons are on the water. 10 electrons. It has that noble gas neon configuration, so just like many other molecules we've seen, they have 10 electrons. But now let's look at the hydronium. Hydronium has 1 extra proton, doesn't it? Because that extra proton got added in. So it makes sense we have 11 protons, but nothing happened with the electrons. No electrons were brought into the system, so we only have 10 electrons. So what is our charge on a hydronium? What is the charge on H3O+? It's a positive charge, a lot like the ammonium, right? Listen to how these names are. Ammonium, hydronium. The ium can often mean positively charged ion, positively charged version of something, the acid version of something. And I already gave away what we have here, but this is the acid, right? Because this molecule has a proton that's been added to it, so that's the acid. Which is the base then? The water is the base. The water is a molecule that has yet to have that proton added, or it's a molecule that has had the proton taken away. So if we want to define water and hydronium compared to each other, the water would be the base and the hydronium would be the acid. What does acid mean again? Acid is a molecule that has a proton that can be given away, and a base is a molecule that does not have that proton yet, but it could gain a proton. Now, it might be very surprising to some people to think of water as a base, but we're going to now see that something even more surprising is true about water. You may start to think of what that could be. Let's look at another thing that water can do, which most people don't realize. Water can also, besides gaining a proton, it can also lose a proton. And now keep track of the periodic table down there. How many electrons were owned by the oxygen? You can count them on the molecule, or you can look at the periodic table. 8 electrons were owned by the oxygen. When we lose that proton, we retain, or we kind of get back, an electron that used to be part of that bond. Now we have 9 electrons that are belonging to the oxygen. Can you think of what charge is that's going to result in? We'll think about that, and then we'll get the answer in a second. This is a very strange looking molecule, perhaps to you, because you're used to oxygens having 2 bonds, and now I'm really challenging these theories that I gave you before. We still do have an octet of electrons, so this is a legitimate molecule. And this is a molecule that is a very famous molecule, actually. It's very common. It's called hydroxide. And what's the formula to the molecule? The formula to the molecule is OH. You can also write OH or HO, same thing. This molecule is hydroxide, and it has 3 sets of lone pairs of electrons. It's not water. It's the deprotonated version of water. It's a version of water that has had the proton taken away. So it's actually the base form of water, which also will kind of clarify that in a second. let's look at what the three different versions of water. So these are all interconverting to each other, which is very interesting. A lot of people are just getting the glimpse in this lesson that chemicals can easily convert from one to another. Acids and bases are probably some of the most easy transformations between one molecule and another, just a matter of losing and gaining protons. So let's look at our water. Water is a neutral molecule because there are 10 protons and 10 electrons. Hydronium is a positively charged molecule, as we saw before, because an extra proton's been added in. So that means that this is the acid form of water, right? That's what acid means. Acid means you have an extra proton that could be given off later to form water again. So what does that make hydroxide? Let's count up the protons and electrons and figure out what the charge is. So how many electrons? You can see there's 10. And how many protons? One less proton than water. So that must mean it has 9 protons, and it still has those same 10 electrons. So what's the charge on a hydroxide? You can kind of see the trend on the right side, positive, neutral in the middle, negative charge, because there's an extra electron. When that proton left, it left behind an electron, and it gave the hydroxide a negative charge. Very interesting, right? So these are the 3 different forms of water. Believe it or not, when you drink water, you're drinking mostly the middle molecule, but you're also drinking these charged ions on either side. A little bit of those are in all water. You can't not drink it. It's impossible to not drink that. That's part of what you're drinking too. You're drinking some OH, you're drinking mostly H2O, and you're also drinking some H3O. Let's look at what these look like in 3D. If you haven't already built these, go ahead and start to build these, and here's what they should look like when you build them. We can't really represent the charge in the model kits, but pretty soon you're going to get used to seeing when you have an oxygen that only has 1 bond, negative charge. If you have an oxygen that's 2 bonds, neutral. If you have an oxygen that's 3 bonds, positive charge. You're going to start to, that's going to become second nature to you. We already know that hydronium is an acid because it has an extra proton added. Water is interesting. We're going to get to water in a second. And hydroxide we know is a base because we know that hydroxide lost a proton compared to water. So then what is water? Water can be an acid or a base. So the fact that water is an acid and it's also a base, this is very interesting. This should start to help us realize that the idea of what an acid is in popular culture, the way you've heard of people talking about acids as something that burns you or something that's dangerous, it's not always true. It's actually mostly not true. Many molecules are not going to burn you, and they're actually something that you have to have in your body to survive. For example, water. Acid has a technical meaning in chemistry. Acid is a molecule that has an extra proton. So hydronium, you might say, is a double acid because it actually has 2 protons that could be given away. Water, you might call it a single acid because it has 1 proton that can be given away. And the hydroxide has this last single proton, which is not normally given away. So hydroxide you might just consider to be a base, but water is in a way a base as well because it has 1 proton that's been taken away when you compare it to hydronium. So naming these molecules, whether it's an acid or a base, it's all relative to one another. So this might take a little bit of time to settle in, but again, you're going to pop these protons on and off to help get us this sense of what's going on here. So if you have the 4-hold oxygens, this is the opportunity to practice the acid-base concept. So if you don't have these, you can also use the carbon or even the nitrogen and just kind of pretend that it's an oxygen, although I really find it's helpful to have the red sphere for this. But build yourselves the hydronium, which is the H3O+. Make sure you have the lone pair or an extra bond sticking up on the top there, and take off a proton. When you hear that pop, you've formed a what? Acid or base. When you take off a proton and you hear the pop of the proton leaving, you've formed a base. When you pop off the other proton, you've formed a double base, okay, right? Hydroxide is really a double base because 2 protons have been lost. Theoretically, you could also lose that last proton, and this does not happen in biology as far as I know, but it can happen in geology. When we lose all the protons from an oxygen, we have what's called a oxide, O2-. You can see that we have a lot more electrons than we normally have on an oxygen. It's a 2- charge. This is an oxide, and many minerals are oxides. Many minerals are oxygens that don't have any protons on them, and they have a -2 charge. But this will cover more when we look at maybe some geological topics in the future. So, but for biochemistry, don't worry about oxide too much. So go ahead and build these guys and practice them a lot, because these are really big concepts in chemistry and biochemistry. I'm now going to do a quick preview of pH. Neutral water, basic water, acidic water. These are slightly different concepts than what we saw before. Acidic molecules have extra protons that can be given off. Basic molecules have that proton has been lost, and that's what a basic molecule means. These terms are a little different when we talk about solutions, taking the pH of a solution and seeing what the pH, whether it's alkali or acidic, basic or acidic, we're going to see what is going on here in terms of the composition of the water. What we have here is a model of neutral water. If you looked at all the molecules here, you see most of these molecules are regular old water molecules, right? H2O. But if we look closely, it's kind of like a word find here, we see that some of the molecules in this neutral water are what? Hydroxides and hydroniums, right? H3O plus and OH minuses. We see there's a very small, it's actually much more exaggerated than this in real life. It's actually an extremely small proportion of hydroniums and hydroxides, but they are there in neutral waters. You can't get rid of them, actually. If you have perfectly neutral pH 7 water, you will always have a very, very small amount of hydroxides and hydroniums. There's nothing wrong with them. There's nothing dangerous about it. This is how water is in reality. That's what neutral water is. Neutral water is mostly water with a very small amount, much smaller than I can really show here, proportion of hydroxides and hydronium. And notice that they're also equal. They're equal because the number of hydroniums, there's 2 here, and the number of hydroxides, there's 2. It's balanced. That's what it means by neutral water. Interesting, right? Let's now look at acidic water. If you have maybe acid rain or some kind of other acid sample of water, it looks a little different. So can you look and see what we have? It's still mostly water, but we do see, if we kind of focus on them, we do see that there's more of one of those ions than the other. Which of the ions do we see here that we didn't see before? We see mostly the H3O pluses, right? We see mostly the hydroniums. We see a little bit of hydroxides, and again, the proportion is exaggerated here. In reality, it's really hard to show the exact proportions because the numbers are logarithmic, and that's why we need the pH scale, but this is another topic. But just for the purposes of a basic idea, acidic water has a lot of acid forms of the molecule, right? The acid hydroniums, which is the acid form of water. That's what acidic water is. Acidic water has quite a bit of H3O plus in it. So what does that mean basic water is? Basic or alkali water. Again, mostly water, but what do we see a bunch of in here? We see a bunch of OH minuses. We see a bunch of hydroxides, a little bit of hydroniums. We see one of them here I drew, but mostly the ion that we see are the hydroxides. This is what basic water is. So this is, I think, a kind of a profound finding for many people to realize, what does basic water really mean? What does acidic water really mean? It's the fact that we have these other molecules, these other forms of water that have found their way into the solution. And we can talk a lot more about that later, but I just want to get that out of the way because this is the kind of question that always comes up. So it's just a good idea to get this preview there. We'll have other lessons that teach in a very strict way, what does pH mean, how do you understand pH scale, and all these other topics. We're now going to look at some other famous acids, some acids that are more typically associated with being acids. We don't usually talk about water as an acid in everyday life, but we do talk about sulfuric acid. It's one of the strong acids. There's a lot going on in this molecule that is a little bit unfamiliar. We've never seen sulfurs with so many bonds, right? Usually we think sulfurs have 2 bonds. These have 6 bonds. How is that possible? We'll go over this in a later lesson. But right now, let's focus on the acid nature of sulfuric acid. How do we tell if a molecule is an acid, or it might be an acid? Remember, we look for oxygens that have protons attached, or I guess nitrogens that have protons attached. But very typically, oxygens with hydrogens attached, these are acids. Sulfuric acid can lose those 2 protons to form its base, which is called sulfate. In chemistry, the ate suffix usually can indicate a base form of an acid. When those 2 protons leave, remember they carry away their own protons, but they leave behind the electrons that used to be part of that bond. So that's what increases the charge on those oxygens to -1 on each one. So sulfate has actually a 2- charge altogether because electrons have been left behind when those protons leave. And if that doesn't make sense to you, go back and keep popping that proton on and off the water molecules. These are very complicated topics. These are things that are maybe covered in high school and definitely are a little bit of a trouble for college students. So if you don't get everything the very first time as I'm speaking it, don't worry about it. You're gonna learn it. Go back and practice it. This is all about practicing, drawing. It eventually will sink in. Let's look at another very famous acid, phosphoric acid. Now, this one we also see a strange bonding on that phosphorus, which we'll cover in a later lesson. But for now, let's focus on the OH part of the molecule, right? So how many OHs are there? How many protons do we have attached to oxygens? We know that when we see protons attached to oxygens, we can suspect they might be the acidic protons that can be lost. What would be the molecule that we form when those 3 protons are lost? So think about it. Think about the charges that would accumulate on those oxygens. We can also pause and think and have the students try to come up with what they think the phosphate will be. But here's our answer. All 3 protons can leave. They can go on and join other molecules. And now we've left with phosphate, which is the base form of phosphoric acid. More examples of famous acids. Acetic acid is very famous. Acetic acid, you've all tasted this. Acetic acid is the active ingredient in vinegar. What is vinegar? Vinegar is a solution of water, some other trace molecules which give the vinegar its specific taste, and mostly acetic acid. Acetic acid is the sour taste of vinegar. Let's look at another very famous acid, citric acid. You probably know that citric acid is the sour flavor in citrus fruits and many other fruits. This is a very complicated molecule. You guys can have fun building this one. It has several protons which can be given off from those oxygens, and that's what makes it an acid. We also have another molecule that's also famous, malic acid. We see lots of protons attached to oxygens. It's the giveaway that we have an acid molecule. It also is sensed by us as a sour flavor. And this is a very sour molecule. This is what gives extreme sour candy their sourness, like Sour Patch Kids or tear jerkers or other kinds of very, very sour candy. Malic acid has been added to it. So the interesting thing for students to realize is that we are actually chemical sensors. Our bodies are kind of chemical instruments. We can sense different flavors, different flavor molecules, and tell the difference between them. We could definitely tell the difference between acetic acid, malic acid, and citric acid just by tasting them. So we are very connected to chemistry. There's another very famous acid. These are actually my favorite acids because if you're a biochemist, these are what you're dealing with. Amino acids are also acids. We see again that we have an oxygen with a proton attached, so we know that's why it's called an acid. We also see a nitrogen, a positive nitrogen with an extra proton that we're used to not seeing on that nitrogen. So this is also a double acid. If we remember ammonium, it's a lot like ammonium, right? It has 4 bonds on the nitrogen. One of those protons could be lost. That's what makes it an acid in that way. Where do we find amino acids? Amino acids are the building blocks of proteins, which are the building blocks of us. We are made of proteins. So in just a few lessons, we're going to learn a lot about proteins. We're going to learn about protein architecture. It's a beautiful, amazing subject. It's actually the reason I created Biochemistry Literacy for Kids, is to teach people how do amino acids come together to make proteins, to make us. What do we have here? What did I do here? We formed the base form of all these molecules. We saw that a lot of those protons can come off. I didn't show all of them coming off. We can actually have one more that comes off the the nitrogen there. This takes a little bit of time to really understand why some of those protons come off and others don't. But the big thing from this lesson is to say, okay, if you have oxygens, if you have nitrogens, if they have protons attached, they can come off and give us change our molecule from an acid to a base. That's the basic idea of the lesson. I'm now going to quickly cover an advanced topic that normally requires a lot more explanation, but I just want to kind of foreshadow it here because some students do ask this question. So the question is, how is it that sometimes a molecule can be in the acid form or it can be in the base form? Why does that happen? So maybe they get that you can have an acid, which is when a molecule has an extra proton or several protons, and a base is when it loses those protons. But why does that happen? The answer has to do with the fact that its environment can change. So let's imagine this amino acid, which it's a nice molecule because it has a variety of things going on. It has carbons with hydrogens attached, which are not acidic at all. It has oxygens with protons attached, which are acidic. And it has this nitrogen with a proton attached, which can also be acidic. So we have a lot of different things going on here. Let's imagine what can happen. We can lose that proton. We can also lose that proton, and the charges are changing and all kinds of things are happening. We can add protons back and we can add the next proton back. But why is that? The answer has to do with its environment. So can you imagine the molecule, this amino acid, in a solution where there are many, many protons? Okay? Doesn't it make sense that if there are a lot of protons around, that the molecule will be completely protonated? It'll be completely in its acid form. So just kind of imagine a classroom where there's a lot of chairs and a lot of people. All those chairs are going to have someone sitting in them, right? Because there's plenty of people around to take up those spaces. That's kind of how acid-base chemistry works. If there's a lot of protons around, the positions where you can have protons attached to your molecule, they'll all be filled up with protons. What if we decrease the amount of protons in the solution? You're going to start to get some of the protons on the molecule to go away. The first one that goes away is that oxygen proton. We have to get into why that is. That's a later a lesson for that. But that negative charge comes back because we've lost that proton, right? That proton used to give us a nice neutral oxygen, but when that proton leaves, it leaves behind the lone pair electron, and we get a negative charge. What if we decrease the number of protons in the solution even more? We actually made an even more basic solution. The molecule will become a fully basic molecule. That last proton on that nitrogen will be allowed to come off, and it will have a hard time coming back. So now imagine a classroom where there's a lot of seats, but not that many people around. The people are the protons, right? So many of the seats will be unoccupied. That's kind of what happens in a molecule that's acid-base active. If there's not a lot of protons around, there will be a lack of protons on the molecule that finds itself in that situation. So that's just an interesting application and kind of going a little bit farther. If you don't get this right now, it's not essential for this lesson, but many students do ask this. So you can have them build this molecule and practice popping on protons and popping them off. And we will get more practice on this later. This is a course that's designed for young students. So if every single topic is not crystal clear, it's totally fine. But that's just a question that I was getting a lot from some of the faster students, and I just wanted to create those slides to acknowledge that. It is an entire unit in itself, so we can cover that more later. It's actually a field called pKa's. That's what you want to, if your students are very interested, look up the topic of pKa's. You will find that. So now for the sake of completeness, I'm going to show you how fluorine reacts in terms of acid bases. We don't really see fluorine very much in biology at all, but it just helps to kind of complete the story here on acids and bases. So we already know how to build hydrogen fluoride, which is also known as hydrofluoric acid. We've seen this from earlier lessons, right? So go ahead and review this. You can draw it again if you need to do it. You can also build this molecule again. We don't have pieces from Molymod or any other company that shows a 4-bonded green piece. But if we wanted to draw this in a more complete way, we would need a piece that looks like a carbon, but that's green, and that way we could represent all those lone pairs of electrons as either using the bond pieces or using the lone pair model pieces. But that's kind of what we should have in our head when we think of HF, hydrofluoric acid. We have a bunch of lone pair of electrons, and then we have one electron pair that is part of that bond. So that's the one that we're going to really focus in on, the one on the left side here. So when we look at hydrogen fluoride, we can also imagine it as an acid form of a molecule. That's the acid form. When we lose that proton, we generate the base form. If we focus at the periodic table on the bottom here, we see that fluorine has 9 electrons of its own. When that proton gets lost, it gains an electron. So it has actually 10 electrons now. So that's what gives the what charge on the fluorine. If you get an electron and lose a proton, it actually means you're going to become a negative charge, right, on the molecule. So that's something we're going to calculate in a minute. This molecule looks a lot like another thing we've seen before. Can you guess which molecule I'm thinking of or which atom I'm thinking of? This looks a lot like neon because it's a single atom. It has an octet of electrons around it. The only difference is that it actually has a negative charge, which we'll see later. But it's a little bit like neon. It's a single atom, isn't it? How do you get the negative charge on the fluoride? Let's calculate the number of positives and negatives in these things. Hydrogen fluoride has 10 protons because there's 9 protons from the fluorine. There's 1 from the proton or from the hydrogen. There's 10 electrons altogether because it has the noble gas configuration. So this is a neutral molecule. We never worried about drawing charges on HF before. But now fluoride, it's a little different. Fluoride has 9 protons because we lost 1 and 10 electrons. So the charge, which wins, the positive or the negative wins. So fluoride is a negative charge. Okay, we can't really make the models of this very well because we don't have all the lone pair, the ability to add the lone pairs, but this is the drawing to match all the others so we can see what is hydrogen fluoride, also known as hydrofluoric acid, and fluoride itself. We know that hydrogen fluoride is the acid because it had that proton to lose. The base form is fluoride because it could gain a proton back. If the environment had enough protons in it, you could reverse this and turn the fluoride back into hydrogen fluoride. That should be maybe a little bit easier for you to imagine. Looking at the definition of acid and base, this starts to make sense again, right? The acid is a molecule that has a proton that can be lost. The base already lost it. And then this is how you draw this. How you would draw this if you were a chemist. You would use the full complement of dots around the F to show the fluoride, and you would draw the minus charge just to show that it's the base form, the negative ion. All right, and again, we can practice this popping on and off. Even if you don't have the pieces that have the ability to place more lone pairs of electrons on them, you can still pop off the extra proton there to show the acid and the base. All right, so go ahead and draw these molecules and practice making them if you haven't done so already. And this is the conclusion of the lesson. We're really getting a much broader understanding of chemistry right now. So this is where we started. We started with looking at these dot structures of the first few elements of the periodic table. We had the 4-3-2-1 rule. We then expanded to the 3-4-3-2-1 rule. This is how we saw chemistry before. But now what we're starting to see is that things are a little bit more complicated, right? We don't always need 2 bonds on an oxygen, 3 on an ammonia, on a nitrogen. We don't always have 1 bond on a fluorine. These things can change based on the environment that the molecule finds itself in. If the water finds itself in an environment where there are many, many protons, we can increase the number of bonds on the water. If the ammonia finds itself in an environment where there's a lot of protons, we can increase the number of protons. If the hydrogen fluoride, the hydrofluoric acid, finds itself in a very basic environment where there's not a lot of protons, that proton can leave and not find its way back, and we can change the number of bonds on the fluorine. So we have actually a variety of forms that these molecules can take now. So this is a new level of sophistication that the students will be acquiring. And these are not small ideas. These are really, really important concepts that happen all throughout biology and biochemistry. These are almost some of the very core concepts of biochemistry. So it's really important for students to realize that these molecules are not static entities, that they really do change based on what their environments, what their environmental conditions are. So this rule that we have here on this block of the periodic table, I'm actually expanding some of the rules for us. So not only do we have the 3-4-3-2-1-0 rule, we have the fact that nitrogen can sometimes have 4 bonds. We know that now. Ammonium can have 4 bonds. What about fluorine? Fluorine can have 0 bonds, just like neon, right? Fluorine can lose that proton. It can act as an acid to form fluoride. What about oxygen? Oxygen is more complicated. Oxygen can gain and lose electrons in some cases. Water is one case like that. Water can gain a proton to form hydronium. It can also lose a proton to become hydroxide. So things are more complicated than when we start, which is great, actually. We want to see the truth and the complexity of nature. So that's really what this lesson is about. Well, thanks for joining me for this wild ride through acid-base chemistry. We're going to expand on this more, and students will become much more familiar with these new and more complex topics as we go forward. So see you in the next lesson.